Since its development, radar technology has been an important part of our society, with applications ranging from air traffic control and meteorological precipitation monitoring to military air defense systems. We would like to introduce to you an exciting and newly emerging field of radar technology, through walls radar. Through walls radar has many practical applications, civilian and military. This technology could be used to assist soldiers clearing a room. It could be used by firefighters going into a burning building so they can know exactly where the people are trapped. Imagine any search and rescue operation with a device that can tell you where people are confined. This technology removes the element of the unknown, which allows these brave men and women to do their jobs in a safer and more effective manner. So how does it work? There are two main components in a radar system. These are a transmitter and a receiver. Usually these are located in the same antenna for simplicity's sake, but this does not always have to be the case. The transmitter sends out a signal which bounces off of the target and returns to the receiver where the signal is processed and analyzed. There are several different methods of radar signal processing. Transit time. This is based on the time of flight of the radio signal. The time is measured from the time the pulse is transmitted to the time it is received. This time is proportional to the distance of the object. Frequency modulation. The radar signal sent out of the antenna is modulated in a predictable pattern. By the time that the signal returns to the receiver, the transmitter frequency will have changed. The amount of frequency shift is used to determine the distance of the object. Frequency modulation is able to be used as a continuous wave radar instead of having to use pulses. A through-walls radar must be able to detect targets behind a solid wall. It must have long enough range such that a user is at a safe distance from any danger behind the wall. The radar system must be portable, and it must be able to output an accurate view of objects behind the wall in real time. The device transmits electromagnetic waves that are able to pass through the wall. These waves must be able to locate the human target and bounce back from the target to the receiver through the wall and display a real-time image on the monitor. This is where we run into the first roadblock, the walls. The signal must pass through a wall a minimum of 2 times, once on the way to the target and another on the way back. Most radar systems are not built to pass through objects, but to reflect off of them. Concrete especially blocks about 99% of the waves that encounter it, so only about 1% of the waves will actually penetrate the wall. The signal is therefore greatly reduced by the time it reaches a receiver. One such solution to this problem is the use of signal amplifiers in combination with picking the right kind of waves to use. Longer wavelengths have an easier time passing through walls than those with shorter wavelengths. However, in order to make longer wavelengths, you would need a larger apparatus. The use of S-band waves is a possible solution to this problem. Because S-band waves have a relatively short wavelength, a large portion of the signal will be lost. But again, this is simply solved with inexpensive signal amplifiers, which take an input signal and magnify it to generate a high-quality waveform. This allows the receiver size to be kept to a minimum. Some questions that have to be considered when designing the device are as follows. How far away can the user be from the wall? How quickly will the signal be delivered? And how clear will the output signal be? When the receiver picks up the signals being reflected off the objects, the wall will appear as the brightest spot on the radar screen, effectively acting as a veil. So the question is how to sift through the signals and ignore those that have bounced off the wall and only process the useful information. The solution? To use crystal analog filter, which shows the differences in the frequencies of different waves. This allows coding-based solutions to separate different objects. Through-the-wall sensing can be considered through 2 points of view. The first, to be able to sense people through a building without actually entering it for reasons such as a dangerous environment, and second, to detect people trapped under debris as a result of a catastrophe. Bodies cause electromagnetic wave reflection, which can be picked up by a radar receiver. As mentioned previously, the challenge is distinguishing between wanted things like people and inanimate objects like rubble or debris. This is done using the same frequency modulation concept as for the meteorological radar. The action of breathing and other body movements create minor Doppler shifts, which can be picked up by radar, more specifically an ultra-wideband radar. Ultra-wideband, or UWB, is used in all through-walls radar systems currently being made. It uses a very low energy level for short-range, high-bandwidth communications. UWB works by transmitting short pulse cycles at specific time intervals. These reflections do not overlap with the original signal. A UWB system has the advantage of being able to tell how long a signal is in flight. Static and inanimate objects don't move, so they won't disrupt the radar signals, and it is possible to track the data of human activity. Moving targets can be tracked by evaluating the differences between their positions and the time that the signals were received. At the distance that a through-the-walls radar system is effective at, radio and other domestic waves would bounce back almost instantaneously to the point of transmission. All these characteristics make UWB useful in the through-wall radar applications. Due to the interference with other signals caused by UWB, the government has placed limitations on the distances they can travel. Different strengths of signals have different limited ranges. Although these signals can travel far distances, their effective range is less than 100 meters due to the loss of signal power through walls. The difficulty separating where signals bounce off also increases as the signals travel and bounce off of more objects, further decreasing their effective ranges. An experiment was done with through-walls radar out of MIT. The image on the left is 2 humans downrange of the radar without a wall between them for use as a control. The next image is 2 people behind a 20 centimeter thick concrete wall, followed by 1 person behind a 20 centimeter concrete wall. The man on the left stood approximately 10 meters downrange, and the man on the right was about 4 meters downrange of the transmitter in the middle image. On the image on the right, the man was approximately 4 meters downrange. One difficulty, however, the study did notice is that the resolution becomes poorer when the people being targeted stand absolutely still, or when they hold their breath. As the course of this project continues, we will work toward modeling and simulating a through-the-walls radar system using MATLAB and the OpenEM software environments. Over the next few weeks, we will be meeting with our professor, Dr. Mohammed Baker, as he helps us discover and explore the possibilities that these 2 environments have to offer. Using the radar equation, we can model a sender/receiver antenna and a point in free space that we will be detecting. We will be able to plot the test point in relation to where our antenna is located. Our second step will be using the Doppler equation in addition to the radar equation to track the point object as it moves throughout space. Once we have managed this, we should be able to apply this to the through-the-walls approach by adding a barrier with properties that are similar to that of a wall and placing it in between the antenna and the object we are trying to track. We will follow in the UWB bandwidth path by finding a wavelength that is optimal for our operation and applying it in short bursts to attempt to track the object behind the wall. In conclusion, I would like to thank you for your time and consideration in watching this video. We will continue to work tirelessly to bring this project into fruition. If you have any questions or concerns for us, please feel free to contact us, as we would love to hear back from you. Thank you for your time.